So we're now interested in looking at vectors in 3 dimensions. We still have all the same sorts of ideas. So a unit vector, and we know every non-zero vector has a corresponding unit vector. We're just basically dividing it by the length of the vector. And you'll notice the formula is exactly the same because vectors are dimensionless. We can use vectors in any dimension. We're just adding an extra component for each dimension. So all the formulas remain the same. We had 2, when we're talking about 2 dimensions, we had 2 special unit vectors, one in the horizontal direction, one in the vertical direction. Well, basically, we're going to use the same idea, but we want 3 unit vectors that are orthogonal. And all orthogonal means is they're mutually perpendicular. Each one is perpendicular to the other one. And again, we're just going to use the horizontal and vertical, but now, well, it's hard to say horizontal and vertical when you're talking about 3 dimensions, but essentially the direction of the 3 axes. In the x direction, remember that was the one that was coming out towards me, that's I still, the y direction's j, but now we'll add in k for the vertical direction. So the component form of a vector, there we go, and there's my vector in 3 dimensions. It's at the point x, y, z. I'm going to call it the vector u. Hasn't changed. The position vector is still that vector going from O to P. Still the same. Yes, now I could write it as an ordered triple instead of an ordered pair, and my column vector would have 3 things instead of 2 things. And if I broke it into component form again, I would have 3 components instead of 2 components. The distance, well, we just saw the distance formula in 2 dimensions, how it changed to 3 dimensions. Well, that's what happens effectively with the magnitude of my vector, x squared plus y squared plus z squared. Now, direction becomes a little bit harder now because I can't simply say it's the inverse tan of the y component over the x component, because I got 3 components now. So we don't talk about it like an angle anymore. We will end up looking at what we call direction vectors. They will go in the direction of a particular vector. So ABCD is a parallelogram. We've got 3 of the vertices given to us. Find the vectors AB and AD. Well, again, it hasn't changed. It's still the same idea of, okay, I'll get head minus tail. So for AB, it will be head minus tail. And this is why I kind of like working with column vectors, because I just read across each row, 18 minus 4, 4 minus 2, 8 minus 3. I just find it a lot easier to work with the column vectors. AD would become that one, minus 5, 10, 10. So I've done that. Well, now we want to work out the coordinates of C. ABCD is a parallelogram, so we know opposite sides are equal and parallel. Well, when we're talking about vectors, that just means they're equal vectors. So AB, the vector AB, would be the same as the vector DC. In a way, I suppose I've written that backwards, haven't I? But head minus tail, so that, okay, C minus D would be the same as B minus A. I want the point C, so I could move the D to the other side. All right, if I play with these position vectors, because effectively, yeah, I'm calling them points, but they're really position vectors, then I'd get the 18, 4, 8, minus 4, 2, 3, and plus the minus 1, 12, 3. Again, because I'm using column vectors, I could just add across or subtract, and I come up with my answer. However, notice it says find the coordinates of C. They're not the coordinates of C. That's the position vector. So the coordinates would be 13, 14, 18. An idea of division of an interval. So okay, we know about midpoint. Midpoint is simply when we divide something in the ratio 1 to 1. You can divide a line in any ratio though. And it might be an internal division, could be an external division. What's the difference? Here's a little bit of a picture to give us an idea. Here's an interval AB. If I want to divide it in a certain ratio, so I'll place P somewhere, and I'm saying it's going to divide it internally in the ratio m to n. So the distance from A to P would be m parts, P to B would be n parts. So that would be an internal division in the ratio m to n. I could have also said it divides BA internally in the ratio n to m. The naming of the interval becomes important when we're talking about the ratio. When it was midpoint, it didn't matter, because 1 to 1 they were equal parts. Here they're not necessarily equal parts, so the naming becomes important. If I say AB, it's the ratio m to n, but if I said BA, it's the ratio n to m. And what about external division? Well, that's when the point is on the line, but it's been produced. So it's actually outside the 2 points, external. So P then, that would be dividing AB externally in the ratio n to n. It's still the same idea. The distance from A to B is m parts, and the distance from B to P is n parts. So that is an external division. Now, if P divided AB in the ratio m to n, playing with vectors, that's how I could pull it all together. Where does this all come from? Well, m plus n, so it's the two numbers in the ratio added together. We end up dividing by that. And the way I think of it is like the numbers have swapped when I'm doing the multiplication. So see how it was AB in the ratio m to n. So I multiplied the A by the n and the B by the m. So I've like swapped the numbers around in that ratio. And A, B and P are of course all the position vectors of those particular points. Let's have a look at one. So I'll do an internal one. I'm going to do this one internally in the ratio 1 to 3. Then that should be my answer. The bottom of the fraction, the two numbers added together, 3 and 1's 4. And then the top of the fraction, swap the ratio around. So it's going to be 3/4 of the first one mentioned, minus 341, and 1/4 of the second one mentioned. And then I'll just add the two together and I come up with the answer, although it did say find the coordinates. So there's our point, 1, 9 on 2, 3 on 2. How do I handle an external one? Another way of thinking about external division is it's a negative ratio. So if I say divides externally in the ratio 5 to 2, that would be the same as saying divided internally in the ratio negative 5 to 2. So if they don't mention internal and external, you always assume it's an internal division. So externally 5 to 2 is the same. I mean, I could have gone 5 to negative 2, negative 5 to 2. It doesn't matter. Just make one of them negative. It's like a fraction. It doesn't matter whether the numerator is negative or the denominator. It's still the same fraction. Okay, now I just pull it together. If that's my ratio now, 5 to negative 2, add them together, I get 3. That goes on the bottom. Swap the numbers. So the first one mentioned, I'll multiply by negative 2. Second one mentioned 5. Add them together, and I have my answer. And notice this time it said find the position vector, so I can leave it as my column vector for the answer. Let's look at this HSC one. And the thing is, you always find it funny that in extension 2 they say, hey, we're playing with 3 dimensions. But then when it comes to this sort of problem, it doesn't really matter. Is that 2 dimensions? Is it 3 dimensions? It's still the same question because we're playing with vectors, and they say vectors, if you like, are dimensionless. Hey, for all I know, this could be in 6 dimensions. Right? Very hard to visualise it, but theoretically it could be. They've defined everything for us there. OA is A, OB is B, PR is some constant times PQ. Let's have a look at that. Oh, that makes sense because it's the same line. So PR has got to be some fraction of PQ. Okay, show this. Really no different to what we were doing in 2-dimensional stuff. It's still the same sort of thing. Okay, let's pull this together. So OP, I can work out. So why did I work out OP? We want to find OR. I got to work out how to get to OR. So I guessed that what I did is I said, okay, I'm going to go to OP, then P to R or something like that. So, but I've got to find some of those things. So OP is 3/5 of OA. We were told that was A. OQ, okay, that's 3B. I can work that one out. OR, that would be OP plus PR. All right, I've got that one now. PQ. Hang on, have I got PQ? No, but I've got OP and OQ. So PQ would be head minus tail. I could substitute that in now, couldn't I? Because head minus tail would become the 3B minus the 3/5 A. I've now got an expression, and yeah, it matches up with the one they want me to show. Okay, now the second part, OR turns out to be a similar expression, you'll notice. It's some multiple of A plus HB, and they've said, look, don't go and do it. I guess in the test they were saying, look, we don't want to waste your time redoing exactly the same idea. So they gave it to us. Show that K is 1/6. So OR, they just told me that. But hang on. In part I, we found it was that, the same vector. So the components would have to be equal. So 1 minus h must be the same as 3/5 1 minus k. So h is 3k. So 1 minus 3k must equal 3/5 1 minus k. And playing around with that, I can get k is 1/6. Find OT in terms of A and B. All right, so OR, I can find an expression for OR now because we know that k is 1/6. If I substitute that in, I get a half A plus a half B. OT is just some multiple of OR, and that must be, they lie on the same line, same idea, it's going to be some multiple of that. So OT is half lambda A plus a half lambda B. So OT becomes OA plus AT, substituting in, we're going to have to equate the components again. 1 minus mu will be lambda on 2. So I now know mu is 1/4, and I can substitute back in and get OT. 3/4 A plus 3/4 B. All right.